Okay, let's get started. So we're in the second part of the class now officially, which is very exciting. Rough outline of how the rest of this semester will go. We'll start by talking about neural network fundamentals, and we'll cover it relatively rigorously, not super rigorously though. And then we will start learning about all different types of neural networks, kind of at like one level of abstraction up. And then we're going to learn about a bunch of things you can do with neural networks. So that'll include predicting with state-of-the-art performance on big data like we've been doing, but then for computer vision, things like segmenting the images, object detection, things like that. And then we'll move to neural networks for sequences, and we'll cover language models and kind of the history of network evolution up to GPT. There's kind of several iterations of language models. And at that point, well, actually before that, after we cover object detection, we'll then have a few coding classes, maybe just one class, maybe two, and we'll go through 4 notebooks. One will be on CNNs for medical classification. We'll go through one on cars that are detecting people in the road, one on segmentation of lungs and medical images, things like that. And then, zooming back out, after the sequence stuff, we'll talk about dimensionality reduction with neural networks. We'll talk about generating, GANs, how do you generate new images of things that you want? And then we'll have even more notebooks. So we'll detect offensive tweets. We will generate fake news. Don't do it at home, but we'll teach you how to do it and give you the code for it. And then we will create fashion, generative networks for fashion, which will be fun. And then we'll talk about reinforcement learning, and then we'll put it all together. And in the last class, we will break down how ChatGPT works, which kind of combines all of these topics that we're learning about in the second half of the class, all in one giant, kind of complex system, but which we'll learn all the components of by the time we get there. So that's rough outline for the rest of the semester. Should be pretty fun. I'll talk a little bit more about homework 4, because you can do the coding part of homework 4 using everything we've learned so far, but you could also do it using what we're about to learn. So okay, let's get into it. So recall from way earlier where we learned about linear and logistic regression, and I made the statement that linear and logistic regression are neural networks. So let's break that down by rethinking about or reframing how we think about these networks. So let's think about linear regression. Let's start with that, and let's think of linear regression. Can't use LR because that could be logistic regression as well. Think of linear regression as the following. So we have our inputs, x1, x2, x3, and we have weights corresponding to each of those inputs, and we're summing up the multiplication between each weight multiplied by the corresponding input. This is what we already know, just a slightly different way of visualizing it. And there's a plus b going on as well. So if we think of a linear regression like this, we could consider this circle thing to be a node or a neuron, like being metaphorical. I don't know if metaphorical is the right word, but you know what I mean. It's an analogy of what we already have learned about. So in thinking of this as a neural network, we can consider this summation thing to be a node, or sometimes less oftenly referred to as a neuron. And we could think of these weights as weights. So the parameters, when we're talking about neural networks, they're weights. Or if you're thinking about it in terms of graph theory, edges, so nodes and edges, just like when you're, in the intro CS classes, when you're dealing with those things. And that gives us y equals w1 x1 plus w2 x2 plus w3 x3 plus b. So we already know about linear regression, but we're just now thinking about it in this way, where we have edges that are multiplied by the inputs and going and summed up, and that's our node. We could think of logistic regression.
Sorry,
Yeah.
edges are just, it's just space, okay.
Yeah. So we could think of logistic regression in a very similar way. Logistic regression as the following. So basically the same thing. We have the summation of all the inputs multiplied by each of the weights plus b. So we have weight 1. I'm trying to be somewhat consistent with the colors, but maybe I'll probably end up forgetting. So we sum them up, and then the only thing we add for logistic regression is we add this sigmoid or softmax activation, depending on whether it's binary or multi-class classification. So here, this is sigmoid for softmax. We talked about both of these before. Activation. So here, activation is a new term of just saying a function that we apply to the output of a node. So let's define that. So activation is a function applied to the output of a node. And that gives us our equation for logistic regression, which in the case of binary logistic regression is just that.
So in this case, is the output the sigmoid or y?
Is the output, it's the same thing. The output of sigmoid is y. And this is just like how we define logistic regression much earlier in the semester. So it's that 1 over 1 plus e to the negative x function. That's called the sigmoid function. And so the above formulation of what we already have learned about is called a perceptron. So above formulation is sometimes called a, quote, perceptron. And so new vocab word, and it's supposedly modeled after what happens in the brain, loosely. So, in our brain, we have a cell body neuron, and then there's these axons that connect to other neurons. And these are called axon terminals. And these output signals from this cell to other cells in the brain. We have a biology class all of a sudden. No, this is the only biology we'll do. And so each cell also has incoming signals from other cells via what are called dendrites. Is anyone studying neuroscience or? Okay, does this check out for neuro? Okay, cool. Incoming signals from other cells. This is how people tell me the brain works. I don't know if this is actually how it works, but supposedly this is how it works. And yeah, so neural networks are supposedly roughly, loosely modeled after the brain. My friends who study computational neuroscience for their PhD are like, it's much more complicated than this, but apparently this is kind of roughly how it works. And so an artificial neural network, today we're gonna learn a lot of new terminology, but then we're gonna use it again and again for the rest of the semester. So an artificial neural network is a set of connected layers of perceptrons. So we'll talk about what a layer means in a second, where the output of one perceptron is the input to the next perceptron. So let's draw this out. So a neural network that's slightly more sophisticated than regular logistic regression or linear regression might have what are called hidden nodes and layers of those nodes. And eventually they output what we're trying to predict. And every node from the previous layer, so let me define the layers really quick. So this first set of inputs is called the input layer. This is called a hidden layer. This is another hidden layer. Again, lots of terminology today, but we'll use it again and again. So it should be second nature by the end of this semester. The final layer is an output layer. So every node in the previous layer in this type of neural network is connected to every node in the next layer. So X1 is connected to the A of the next layer and the B of the next layer, but the X2 is also connected to the A of the next layer and the B of the next layer, and the X3 is also connected to the A of the next layer and the B of the next layer. So these are all weights that the model learns. So let's give them names. Weight 1, weight 2, weight 3, weight 4, weight 5, and weight 6. But then in the next layer, or connection between layers, the nodes are connected in the same way. So we have weight 7, weight 8, weight 9, and weight 10. And then we have our output node, which is only a single node in the case of binary classification, which, because we had that sigmoid activation, it's a number between 0 and 1, just like in logistic regression. And in this example, we have weight 11 and weight 12. So we'll, let me think about the order. So let's think about what if we're training this model, what function is this modeling? So y, the output is weight 11 times c plus weight 12 times d, using the same basic setup of logistic or linear regression. You're just multiplying each input by the weights going into that node. So we're doing the same thing. This output node is the multiplication of each weight from the previous, each node of the previous layer, and then adding those all up. Are we good so far? So does the statement y equals W11C plus W12D make sense given how we set up a perceptron? Okay, so we could expand that to be, oh, by the way, I think after today it's gonna get much less mathy because we're gonna build, like these will be the building block for a bunch of other concepts, and basically they all build on this. So we're gonna cover some math today, and it'll be the basis of the rest of the semester. So W11, if we expand C, well, what's going into C? Well, it's W7 times A plus W9 times B. So W7 times A plus W9 times B. And we could also expand D in the same way. So D is W8 times A plus W10 times B. Okay, are we comfortable with this so far, this expansion? Okay, so final expansion equals, well, actually, so et cetera, and what you end up with is W11 times W7 times W1 times X1. Here, let me put a ... here. I recommend that you do that expansion on your own, if you want, times X2 plus W11, W7, W5, X3 plus W11, W9, W2, X1 plus ... Let me actually, change my mind. Let's just do one more expansion between here, and I'll do the ... at the end of this final equation. There's a point to this, I promise. Equals W11, and now we're gonna, we have big parentheses, W7 times A. Well, now we have to expand A. Well, what's A? A is W1 times X1 plus W3 times X2 plus W5 times X3. So W1 times X1 plus W3 times X2 plus W5 times X3 plus W9 with B expanded. Well, what's B? It's W2 times X1 plus W4 times X2 plus W6 times X3. W2 times X1 plus W4 times X2 plus W6 times X3. Okay, we're halfway there on this expansion. So we've expanded the W7A plus W9B part. Let's do the same thing for the W12 outer term. This is super tedious, I know, but hopefully it's not complicated, just tedious, which is never good. Usually it's better the other way around, but that's okay. So A has the same expansion, so we actually don't have to, we could plug in the same thing. Because we again are just putting in putting A into this parentheses plus W10 times B, which is the same as before, W2X1 plus W4X2 plus W6X3, close parentheses. And then that comes out to be this thing, and you just redistribute terms and distributive property. So the observation to make for all this is that, well, isn't this just a linear function? And so why are we doing all this if this is just a linear, wait, isn't a linear function, sorry, isn't this a linear function? Why not use linear slash logistic regression? Because all we're doing is learn, W11 times W7 times W1 is just another weight, another constant. And so we're just learning a constant times an input. What's the point of doing all this? Well, that's a good point. If this is where we ended, there'd be no point to neural networks because how we formulate it so far is just learning a linear function. So the answer to this is that we want to add non-linearity somehow to the network. And the way we're going to do it is going to be powerful enough to allow the network to learn any function ever, which is good. So what we do is we take each node's output, take each node's output and a non-linear activation function. We're using that term again. Activation function to, and a popular, maybe the most popular activation function, and we'll see why in a second. So a popular activation function is called ReLU, which stands for rectified linear unit, which is a super fancy way, common theme in machine learning, fancy way of describing a simple concept. It's just this function. So x is the input, ReLU of x. It's just, if x is negative, then we have 0, and if x is positive, then we just have x. So when people try to be fancy and say rectified linear unit, they just mean that. So ReLU of x could also be written mathematically as max of 0 and x, whichever one's larger. And that is 0 when x is less than 0, and x if x is greater than or equal to 0. Two different ways of writing the same thing. So let's look at what the effect would be in a neural network, and then we'll talk about why ReLU and functions like it are so important to a neural network. But first, just an example, small example of what it does. So let's say 5 and 4 are the inputs to this network, and the first hidden layer has 2 nodes, and let's say the network happens to have learned these weights through the learning process, which we'll talk about in a bit. So let's say the weights happen to be -1, 0, 1, and 2.
Sorry, could you specify what that first circle is again?
Which what?
So right here, like the first, so like 5 and 4 point to like one circle block.
Mm-hmm.
So what is that a hidden layer or is that the input layer?
Yeah, let's let me clarify. So this is, oops, wrong color. This is x1, this is x2, and so, yeah, and then everything else would be a hidden layer. So the output of this node would normally be well, -1 times 5 plus 0 times 5, so that's -5. And the output of the second node would be 0 times 5 plus 2 times 4, which is 8. But now we apply ReLU to the output, and that gives us 0 here. We apply ReLU to the output, and that gives us 8. And so what we propagate forward in the network are not -5 and 8, but 0 and 8. So you're probably wondering, okay, why are we doing all this? Well, activation functions, including but not limited to ReLU, activation functions allow, let's say, like ReLU, but not just ReLU, allow these networks to learn any function, in parentheses, given enough nodes and edges. And in other words, it can approximate any function. So you're probably wondering, well, why is that? Well, let's draw out an example. So let's say we have, on the x-axis, I'm going to draw x. And on the y-axis, I'm going to draw ReLU of some parameters multiplied by x. And for maybe one parameter set, which I'll draw in blue, so this can be parameter set 1, we have the output of ReLU gives us this function. For another parameter set, let's call it parameter set 2, the output of ReLU gives us this function, because the theta 0 plus theta 1 x1 plus ... gives us a negative number, and so the ReLU of that gives us the inverse. It gives us a negative number for larger numbers of x, that is, and a positive number for smaller values of x. So with that parameter set, we might get this ReLU activation. And for a third parameter set, we might get this ReLU activation. And let me erase this extra red. Okay. Oop, whoa. Too much erasing. Okay. So if we add these all up, as we do in neural networks, so when adding these up, we get, so now I'm gonna plot as the x-axis x, and on the y-axis I'm going to do the sum of the three functions above. Well, okay, up to this point, it's pretty easy. We get that shape up to here, and then once we get over here, we start just increasing linearly until we get here. And then when we get here, we're adding both of those lines together. So, and hopefully you can see, I'm not doing some rigorous proof or anything, but if you keep adding functions where you can have any slope going this way and any slope going this way, and you keep adding them up, you can get any function with that, given enough of these functions. I'm not doing a proof, but it's pretty intuitive, right? You just have, if you have infinitely many lines, you could approximate anything, right? You just get smaller and smaller lines with more nodes. So let's just write that out. if you add infinitely more functions, you can approximate anything. And this is called the universal approximation theorem. And there's a lot of math behind it, etc. But you get the idea. In this class, we're going to start moving fast and cover all the cool things that neural networks can do. So let me now define what deep learning is. So deep learning is where we have many, many layers. So when you hear deep learning, that's a neural network with many layers. Neural net, for short, with many layers. Do I need to draw that out, or does that? So, you can imagine you have 50 hidden layers or hundreds of hidden layers. That is deep learning. It's deep because there's many layers. And so you might be wondering, why do we need deep learning if that universal approximation theorem is telling us that we can approximate any function if we just have enough nodes in that hidden layer? So good question. So why use deep learning? Let me start adding some abbreviations. So we're going to use NN for neural net, and we're going to use DL for deep learning. These are pretty common abbreviations. Okay, so why use deep learning when we can approximate anything with one hidden layer? What's the point of, why would we add more layers versus just adding more nodes within one layer? So the answer to that question is that deep networks need exponentially fewer parameters to achieve similar performance. So, and I'll show you why visually in a bit. So deep networks need exponentially, there's a lot of English writing today just as we define things, but that'll stop pretty soon. So deep networks need exponentially fewer parameters to achieve similar performance. And so let's just get some intuition on why that might be the case. Oh, sorry, I thought there was a question. Oh, go up.
Thank you.
Oh, sure.
I have a question.
Sure.
So deep learning is with multiple layers, but do we ever have a scenario where we would want multiple input or output layers?
Yeah, so there's a whole field. I wasn't planning on covering that in this class because there's only so much, but there's multimodal learning where you want to learn from multiple types of inputs. So you might want to predict one thing and learn from image and audio at the same time, for example. And so one layer is the image layer and one layer is the audio layer, and then you go through deep learning and then you connect them later on.
Oh, so each layer is like a type of information.
No, that's, sorry, maybe I shouldn't go into that because it's just you can modify this to make it work with multiple inputs. But yeah, for today, for today, no. But yes, but
In reality,
yeah.
yes.
there's no way to go into that with what we know now, basically. Um, so, let's say that we are, we have this network and we have two hidden layers. So I'm just going to draw it like this for short. So this node is f of x1 comma x2, and we'll say that this node is g of x1 x2, where it's just theta plus theta 1. That's the f of x, and g of x, just different thetas. So if we have a second layer, so as we go more deep in the network, what we're able to learn is functions going to allow you to learn more complex things than if you just had 4 functions on their own. So basically, as you go deeper, you're able to use previous layers as building blocks to more complex functions, and you essentially have these reusable components that make it easy to, you get increasingly more nonlinear and complex functions deeper. And so you don't have to recalculate things as much. You can do complex calculations using previous layers as building blocks or function components to these more complicated functions. And what this ends up doing in practice, so let's just write that first statement. First, stacking layers allows using prior layers as modular functions, and so you can create more complex functions with the same amount of weights, same number of weights. And what ends up happening is that progressive layers learn more high-level / abstract concepts. And we'll see this idea again and again in this class. But yeah, that's why deep learning is often popular instead of just a neural network with one hidden layer. Okay, any questions so far on the setup of like what a neural network is? And given that the weights have been learned, how we make a predict, or what the output of a neural network is, given that the weights have already been learned. Okay, so the last part of this is how are they trained? So how are neural networks trained? And answer is pretty simple. It's gradient descent, just like before. So that's why we spent all that time on gradient descent. It's used for neural networks. Neural networks are the most popular thing and most powerful thing these days. So recall the general equation for gradient descent, where we update each weight of our model by some learning rate times the partial derivative of our loss function with respect to that particular weight. But we have a little complex situation here because all the weights are layered. So, but the weights are layered, which is a different scenario than we had before. So, for example, if our output E, error, depends on a prior set of hidden nodes C and D, which depend on a prior set A and B. And just quickly draw those weights. Dot, dot, dot. This could be a much deeper network. Just drawing the end of the network. Well, let's say, let's give some numbers or labels to these weights. So if we wanted to update, say, weight 1, which is kind of in the middle of the network, we would want to, well, we'd have to, by the definition of gradient descent, calculate the partial derivative of the loss with respect to weight 1. But that depends on weight 5 as well as C and E. So all these nodes and weights that are in between the weight that we're trying to calculate the partial derivative for and the loss all affect that loss calculation. So what we can do is use the chain rule, which I don't think we quite covered in our, sorry, 1 second. I don't think we quite covered it in our, see if I can talk with this, in our calculus review, but quick review.
Sorry, is that W5L?
Thanks. W5, comma. Oh yeah. C. So chain rule from calculus. Let's say we have y equals f of u, where u equals g of x. Then the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. And that's from Calc 101. So we're going to use this in this chain rule when training use networks, or so when calculating the derivative of the loss with respect to each weight. I think the easiest way to see how that works is just to look at a short example. So back prop example. And for this example, we're going to look at a really small neural network. So x1 and x2 are the only inputs. Oh, by the way, there's always plus b's everywhere. I'm just eliminating those just so it doesn't get out of hand. But just imagine there's a plus b still floating around. Okay, so we're going to call our hidden node before ReLU activation as z. And then that will go through ReLU activation, which sometimes is denoted with this sigma symbol. So I'll just use it here because that's kind of a convention that has sometimes been used. And then we'll, for simplicity, just have one output node, which goes through another activation, although in this case, this would be the sigmoid or softmax activation, and that will give us the loss. And now I'll draw all the weights in red. So we have that weight, that weight, that weight, and that weight. So these are the weights of this relatively shallow neural network. So we'll label it weight 1, 2. Actually, sorry, I messed that up. Weight 1, 1. So it goes from x1 to z1. Weight 1, 2. Weight 2, 1. And weight 2, 2. And then I'll just label this weight 3, 1 and 3, 2. Not super consistent, but that's okay. And we'll point out that these activations are ReLU, and this activation is sigmoid. And so, using the chain rule, let's start with thinking about what, if we wanted to update weight 3, 1, so partial derivative of the loss with respect to weight 3, 1, well, to get to the loss, we have to go through the sigmoid activation. That sigmoid activation is a function of the output node Z3, and Z3 somewhat depends on weight 3, 1. So we can use the chain rule because we kind of have this function of a function of a function situation going on. And so just using the chain rule, partial derivative of the loss with respect to the output of the sigmoid function times the partial derivative of the sigmoid function with respect to Z3 times the partial derivative of Z3 with respect, oops, I forgot the with respect to W3, 1, because each of those things in the network is depending on the previous thing. So therefore, we just apply the chain rule. So that one's, let's do one more. So we'll apply the chain rule one more time, but let's do it for a weight that's earlier in the network now. So let's do it for a weight 2, 1. So that starts off similar, which is an important note that we'll come back to. So partial derivative of the loss with respect to that sigmoid activation. We start at the end of the network, and that would be multiplied by the partial derivative of that sigmoid activation with respect to Z3. So we've gone back here in the network. But now to get to weight 2, 1, we notice that so we're not really updating other weights. We're only updating weight 2, 1. So we're taking the partial derivative only with respect to weight 2, 1. So we don't consider that weight in our calculation, and we go to the partial derivative of Z3, not with respect to weight 3, 1, but with respect to the output of the previous function. So that would be the ReLU activation, and we multiply that, the partial derivative of that ReLU activation with respect to Z1, which is right before it, and then the partial derivative of Z1 with respect to the weight that we're interested in, weight 2, 1. So these are the types of computations that we make. And you'll notice in a really large neural network, a very deep neural network, we have several layers. We're going to have to do a giant partial derivative where we're multiplying many terms. So,
Sorry, I'm confused. Why do we not do the similar, I guess, chain rule in the previous case?
in this first one,
Yeah.
because we're only looking at weight 3-1, and so we haven't. So if we're looking at how the loss changes with respect to weight 3-1.
Oh, we're going back one layer
y-
in the next case.
Yes, yeah.
Oh.
So weight 2-1 is one layer before. Sorry, there's another question. This way?
Yeah, how could you take a derivative as z3 with respect to sigma 1? Because it's a relative function and it's a non-derivative function. So how could you take a derivative over a non-derivative function?
Yeah, I won't talk about that now. That's a little bit too much math. But it's these are all very computable. So let's observe that this is already computed in the previous step. So already computed in the previous step. So because as we go deeper in the neural network backwards, we already ended up pre-computing the multiplication, the product of these partial derivatives through most of the layers ahead of it. We could reuse those computations. So we can use dynamic programming, which is a core computer science concept that we won't talk about, but it basically means cache the results of prior computations. So I'll just write that, to cache results of prior computations. And so backpropagation, I guess I haven't defined backpropagation. Why didn't y'all tell me? Okay, so backpropagation is basically a way to make the calculation of these partial derivatives that are important, that need to be made for gradient descent, much more efficient. So basically we're starting at the end of the network and computing the partial derivatives back through the network and caching the results as we go. So from now on in the class, I'm going to draw these types of neural networks with the simplified way of drawing it. And yeah, so like layer, input layer, hidden layer 1, hidden layer 2, output. And so what happens in backpropagation, often abbreviated just as backprop, is that we compute these weights first, and then we compute these second, and then we compute these third, and each time we reuse the partial derivatives in the previous steps so that we're only calculating a couple new partial derivatives. Okay. So that is the basics of one type of neural network, which are called multi-layer perceptrons. So we said that the way of formulating linear and logistic regression is a perceptron. When we have many perceptrons in many layers, we call that a multi-layer perceptron, often abbreviated as MLP, or some people call it a dense neural network, just different ways of saying the same thing. So multi-layer perceptron, dense neural network are I'm just going to call it the basic type of neural network we have learned about so far. And so all the topics we're going to cover build upon what we've talked about here. We have nodes that are connected via weights, and we train it with gradient descent, which is probably not too novel at this point in the class because we talked so much about gradient descent and training weights and the gradient descent process before. The only thing that's different is that we have these more complex models with multiple layers that can now approximate any function due to the universal approximation theorem. And when we train them with gradient descent, because we have to calculate all these derivatives, we use this optimization called backpropagation, where we save the prior computations of the partial derivatives so we don't have to reuse them while calculating earlier derivatives. Okay, so if there's not any questions, let's move on. So you might be wondering, why do we, like, random forests or decision trees could already approximate any function, so why do we need neural nets to approximate any function? Because random forests already did that for us, and SVMs could do that too with the right kernel. Yeah, it's a good point. And for a while, actually, when neural nets were first invented, they existed for a while, possibly before SVMs. I don't quite, don't quote me on that, but it's a possibility. But even while neural networks existed, SVMs outperformed them for a while, and sometimes decision trees did too. So there's two reasons. The first is that computational power. So neural networks are pretty expensive to train because you're calculating, even with backprop, all these partial derivatives. It uses a lot of computational power. And until the mid-2000s, there just wasn't enough computational power. So this theoretical idea existed in theory, but there wasn't the computers to implement it. And so no one was able to make really deep neural networks with a bunch of nodes per layer that would be able to learn these complex functions. So even though the idea existed, no one was able to actually implement it, or they could implement it, but it wouldn't run. And so there was kind of no point. But, computational power is growing exponentially. And so now we can, and that only started in the mid-2000s. That's the first reason. The second reason is that the neural networks that we've learned so far, multi-layer perceptron and dense neural networks, not so exciting on their own. They're kind of the basis for a lot of other types of exciting neural networks. So we could take this general framework. We have layers, we have weights between the components of the layers, and we're training it with gradient descent with backprop. Take that basic formulation and start making tweaks to specific things we want to do. And because this general framework is so extendable, we're able to learn models that can do more than just predict things from data. They can start to do other things that are really powerful. And the first of these that we're going to talk about a lot of extensions to this basic framework. For the rest of this class, that's basically what we're doing. We'll talk a little bit about reinforcement learning as well, because it's cool and it's actually required for understanding ChatGPT. But along with all this, but the first one we'll start with is called convolutional neural networks, which does predict things really well, but it does a second thing really well, which is it automatically learns the best features to extract. So far, and for homework 4, we've talked about how you can use engineered features to extract features. So you can say, I'm going to take the image or whatever, and I'm going to get these specific features in this specific way. I'm going to use this specific filter or kernel, or I'm going to take PCA and use that as the input to the model, or all these different ways you can transform it, where the transformation you're making is guaranteed to be the same given each input, and where you know exactly what that transformation is going to do. But neural networks changed all that, because you can change neural networks a little bit so that they learn the best features to extract automatically. So you're not extracting edges and saying, oh, I think that edges are probably the best things to extract, and that'll make prediction easier. You instead have the neural network learn it, and maybe it's learning things that you can't even see because you have human eyes and perception, and that biases what you think. But it automatically learns the features to extract that might be unintuitive, might be crazy complex, might have, like this pixel might be really important in the context of this pixel, but you would never know it just by looking at it. But because it's A, so small, and B, it might be this crazy relationship, and imagine that happening for all the pixels, etc. So that's the first cool thing that neural networks allow us to do, is automatically learn features to extract. So no more hand engineering features, except in homework 4. Although in homework 4, you can use the type of neural network we're about to learn about, because we're learning about it starting now, and you have a while before homework 4 is due. So this is an option. But other options you have are PCA. That's actually a popular method for face recognition, which is the coding task. It's you code the representation of the input data for face recognition. Doing PCA on those images is a common feature representation. That's called eigenfaces, implemented in some popular libraries, I think. So just Google eigenfaces implementation. You can use that for homework 4, or you can do other types of dimensionality reduction, which come in scikit-learn. PCA comes in scikit-learn too, by the way, so you can just, well, don't tell yourselves, but you could also check your answers to that PCA question by just putting it in scikit-learn and seeing if you get the same answer as scikit-learn. But you could also just call the scikit-learn PCA and use that for homework 4. If you Google feature representation images scikit-learn, there'll be a lot of options like HAR cascades, SIFT. There's other libraries you can use, OpenCV. But all these methods are deterministic methods, and they're very specific, and they're just humans saying that I think that when you change the image in this way, it'll be easier to predict because it won't overfit. Convolutional neural networks automatically learn features. So convolutional networks of the neural variety. CNNs. And so let's just end on a short review of what we talked about, and we'll build on this, but what we talked about in the feature engineering lecture, which is recall that we can extract visual properties of an image through convolutions. So we drew this, a while ago, but CNNs require understanding this concept. So just reviewing it again, we had this kernel matrix, and I showed you that website, setosa.io/something, that showed the effects of different kernel matrices, when you slide it across an image and take the dot product at each position and use each dot product, which is a scalar, a number, as the corresponding position in the resulting image. So there was a reason we talked about that and showed that website. It's because it's important for CNNs. So we take the image and we apply that process and we get back the filtered image. Do y'all remember this? Okay, so I don't need to talk too much more about that. And then I guess the other thing to recall, and then we could move on, is that kernels are specialized to filter images differently. So, like, for example, we saw that there was the outline kernel, which kind of looked like this, had a relatively big number in the center and negative ones around it, which when you take the dot product of the pixel in the center there, will make the center pixel really dark and the pixels around it much lighter. So that has the effect of outlining the image. We saw that with the demo. We also saw these are all hand engineered, by the way. We also saw that there's a blur kernel where if you just weighted average of all the pixels in that region, it kind of meshes them together and that blurs. If we do kind of the opposite, we can sharpen the image.
Sorry, are these all filtered image matrices?
Yeah, these are all different kernel/filters. Where these are all different versions of this thing that could be slid across the image. Convolved is what we called it, applying the convolution, where we do the dot product between each portion.
Sure.
So, yeah, traditionally, and when you first take a computer vision class, well, probably not anymore, but back in the day, you would learn all these kernels that do specific properties. But, actually, let's draw, because we'll use this repeatedly, let's draw out this process a little bit more. So, like, let's say this is our input image. We would have our kernel start off in the upper left-hand kernel corner and take the dot product between the kernel and that patch of the image. That would give us a number. And then we slide over that same kernel a little bit in the image, take the dot product, and that will give us a different number. That'll go in that corresponding pixel in the next image. We can keep going. I won't draw all of that, but after you go through the first row, then you slide down, you start doing the same thing, and that would give you that corresponding part of the next image or the resulting image. Do that throughout until you get a new image where you've calculated each pixel of the new image individually using that convolution operator. So each pixel in the new image is the dot product between the kernel and corresponding image portion. So the key ideas of CNNs, given what we talked about before, so that was all hopefully review from our feature representation lecture. So the key idea of convolutional neural networks is that, one, we use several kernels. So different kernels will extract different aspects of the image, different features, that is. And two, we will automatically learn the best kernels to use. So we're not going to just pre-specify the kernels. We're going to use the gradient descent process to learn these best kernels. So i.e. best features to extract. Our convolutional neural networks, as you could imagine, are traditionally used for computer vision, but they are also now increasingly used in many other types of inputs as well. But we'll start off by talking about them in terms of computer vision, because that's by far the most popular. So the idea of a convolutional neural network is roughly similar to the dense neural network we talked about, except we start off with a convolutional layer. So convolutional layers, a new type of layer. And this is going to be a recurring theme, is we're going to take that general framework we learned and learn about new types of layers that do different things. So this is the first new type of layer that we're learning about. And then eventually you can just connect them all, kind of like Legos, which is fun, to do different things that you want to do. But okay, so we learned about one type of layer, the dense layer, bunch of nodes and edges. New type of layer is a convolutional layer, which takes some input, and that could be a grid, could be a matrix, a grid, could be a 3D version of that, a tensor, same tensor as TensorFlow, 4D, 5D, but for images it tends to be 3D. We'll come back to that. But we have, convolutional layers have kernels, and so kernel 1, kernel 2, ... kernel, let's use K, and we slide each of those kernels across the input image, and that gives us a resulting set of what are called activation maps. So could draw it maybe like that, where there are going to be K of these activation maps. Almost done for today. So K of these activation maps, where activation map K is formed through convolving kernel K across the input image. So that was kind of fast. We'll review this again on Tuesday and then start building. But this is kind of the start of how convolutional neural networks learn. So we'll end there.